the way you do that is, right, so you took 2 and minus 2, right? Now, if you are willing to go and work with imaginary numbers, right, then things will start, flipping in other places, right? So, for instance, you think, okay, A2 is always going to be positive, right? The A2 is always going to appear in the positive thing because the value is square. But if the if the point is imaginary, then this term can become negative, correct? So instead of choosing all real points, the idea in the Schoenhage's Strassen algorithm is that you basically choose points which are imaginary. Okay? In particular, you choose complex roots of unity. Right? So once you are with complex numbers, you can take minus 1 to the power 1 by 100, right? Or the 100th root of minus 1 is still defined, right? And by working with those, then you can make this divide and conquer approach work at every level, and then now you will have an algorithm which will have the recurrence of, you get something that says something like this, 2t of n by 2 plus O of n, and if you solve that, that is just an n log n algorithm, right? So, yeah?
What do you mean by complex root of unity?
Complex root of unity. So square root of minus 1, right, is the 4th root of unity, right? 1 to the power 1 by 4 has many values. One of the values is square root minus 1, right? Because square root minus 1 to the power 4 is 1, right? So that way you can keep defining, and if you remember complex numbers, you will know that square root of I, right, is still another complex number, right? And there is, in your textbook, there is a nice discussion of, with the unit circle and the complex plane, and how do you define the nth root, and in fact, it's quite easy. So you know the complex plane, right? So this is the imaginary, and this is the real value, right? And then you have the unit circle, because the value, the magnitude of this number is always 1, right? So you can, if you want the nth root of unity, then you take this circle, divide it into n pieces, right? So this angle will be 2 pi by n, okay? So this, so everything that is at 2 pi by n, each of those values is an nth root of unity, okay? So, so again, the matrix form using the fast Fourier transform looks very similar to what we saw before, except that instead of evaluating at x0, x1, and so on, we evaluate it at 1, the nth root of unity, and various powers of the nth root of unity. Okay, so we do that, and then, but otherwise the matrix representation basically is the same, right? You have the same coefficients right here, and you evaluate it at these points, which is omega, omega square, omega cube, and omega power n minus 1, where omega is the nth root of unity. Okay, so where n is the capital nth root of unity that we're talking about. Okay, so the FFT-based multiplication algorithm is basically very similar to the two algorithm that we talked about, except that instead of, you know, picking a particular value of n and choosing, you know, real valued coefficients that somehow, you know, make everything efficient, there is a more systematic approach here. Okay, not to say that this doesn't have its own disadvantages, but it does have some benefits that, at least in a theoretical sense, will get you a better asymptotic complexity than what you can get with the Tomb algorithm. Okay, so because of this recurrence relation, we have this n log n time algorithm we can get, whereas the other one has, you know, n to the power something, right? So if we have in the Tomb 2, you'll have n to the power 1.59, and then you know, if you go to the next level, the exponent decreases a little bit, and I don't remember exactly what it is, but it decreases gradually as you increase the number n. But once you increase the number n, as I said, the constants involved will become larger and larger. So the benefits, what that means is that, well, you know, the benefits are not going to be as impressive as the exponent decrease suggests. Okay, so this is saying the same thing. So once again, you know, you use this matrix multiplication to do this, but because we are doing this matrix multiplication using this divide and conquer strategy, this multiplication here doesn't take too much time. It only takes n log n time. Okay. And again, once we have the points, you want to invert it. Once again, you have a matrix multiplication, and once again, that is going to be you know, n log n time, right? So that's why you have n log n, and then a pointwise representation where you have O of n multiplication, and then so on. Okay. So so again, so fast Fourier transform is a technique that has a wide range of applications. So I have like 25 slides in the lecture notes on FFT, right? Any of you who might have some interest, I recommend that you go through them. But for those of you who don't have any motivation to look into that, that's fine. Okay, it's not something that I'm going to expect you to know, right? I just want to say that FFT is thought of as a signal processing technique, right? So for instance, if you think about, you know, you listen to MP3 music, well, how is MP3 music, how is it encoded that way? Okay, so what you do is you take a waveform, somehow break it into its different harmonics, in a sense, right? And then you express it as a series that says at different frequencies, this is the amplitude of the sound at different frequencies, and you sum that up. So that is a way to essentially represent any sound. Now you can start working with these coefficients, and once you work with coefficients, you know, then you can make the connection between that representation and the polynomial representation. Okay. Now, so let's just you know, sum up this FFT-based multiplication. Okay. So in reality, you cannot work with complex numbers, right? Complex numbers means they are real, right? They are real valued, and real valued numbers cannot be represented without loss, without precision loss on our machines, right? So what do we do? Okay, so there is actually a way to deal with that. So instead of working with complex numbers, you can work in a different setting. Okay. So how many of you have heard of concepts such as groups and rings? So it's not unfamiliar, right? So group is, so this is a side discussion. So don't ask me, is this going to be in the exam? No, it's not going to be in the exam. But I assume that all of us are curious and would like to know, see the connections between you know, different things that we learn, right? So what is a group? A group is a set with, right, set with an operation plus. Okay, we'll call it plus, right, with three properties, right? Set is let's say binary operation, right? Closure, which means that, you know, A plus B
is an element of
set,
the set.
let's call this a set A, right? So if you take two elements A and B and you apply addition, then the result should be in the set, right? Then you have identity element, right? So there exists an identity element such that I plus A equals A for all elements, right? And then you have associativity, which I presume everybody has heard of. What is associativity property, right? So you need these three properties. No, there's also an inverse property, right? So you need a okay. So there is also an inverse element, right? So A plus A inverse equals A inverse plus A equals the identity element. Okay? So obviously, if you think about integers with the addition operation, right? So that is a group, right? So where this plus is the addition, 0 is the identity element, and for a number n, minus n is your inverse, right? So that is a group. So then we define something called a ring, where in addition you have a multiplication or this is a group plus another operation binary operation that we will call a star. Okay? So now the additional conditions are the distributive property, right? And I believe there is associativity. No, the group has to be, the plus has to be commutative. So there are a few more things. So if you want an example of a ring, polynomials, right, is a ring, right? So if you have polynomials, then polynomial addition and polynomial multiplication, right? So those operations together form a ring. Okay. So of course, integers with addition and multiplication also form a ring. Okay. Now, to get more structure, you go to what is called a field. In a field, you also insist on multiplicative identity and inverse. Okay? So you know that on integers there is no multiplicative inverse, right? If I give you 7, what is the multiplicative inverse of 7? It's 1 by 7. That's not an integer, right? So so integers don't form a field, but rational numbers form a field, right? So now, essentially what we need is we need to work with a field. It doesn't really matter that it is, complex numbers and so on, right? We just need the appropriate structure, right? In fact, you can work with just rings, and you just need the appropriate structure in that domain or in that set, right? And the appropriate definition of these operations, and then everything would work fine, right? So one way to get the appropriate structure with the properties that you want is to work with modulo arithmetic. Okay, so which means that you're going to, for instance, if you say mod 33 arithmetic, right? So that means 2 times, if you take the product of 2 times 17, right? So you're going to do modulo arithmetic, which means that it's going to give you value 1, right? Because 2 times 17 is 34, 34 modulo 33 is 1, right? Similarly, 17 plus 20 equals 4, right? Because 37 modulo 3 is 4, right? So once you have that, if you choose it appropriately, then you will find that in that structure you can get roots that you want, right? So for instance, if you compute 2 to the power 10 using modulo 33 arithmetic, you will find that it is equal to 1. Okay, so the 10th root of unity exists in this structure. Okay, and now you can start working with that type of a structure instead of working with real numbers and so on. Okay, and this is exactly what one has to do in order to apply this in the context of if you want to apply a FFT-based technique for integer multiplication, it's necessary for us to work with lossless representations, and therefore we need to work with these types of structures. Okay, and then there are a few more details. You're trying to add lots of numbers and so on. So in fact, what I said as n log n is not exactly n log n. If you look at it more carefully and account for the fact that you have to do additions of large number of numbers, then you'll find that it is n log square n. But in fact, there is a further cleverer way that I'm not even going to try to give a flavor of, which reduces this log square n, right? So the second log n is reduced to log n, right? So that's better. But on the other hand, you can also see that log n is often not a particularly big number, right? Okay, so that's the summary of multiplication, right? So if you look at some libraries for arbitrary precision arithmetic, they will end up using a combination of various algorithms that we talked about. So GNU-MP is a popular library for doing these things. So so it uses starts by using naive multiplication for small number of bits in the range of hundreds of bits, and then it goes to Karatsuba, and then TOM 3, TOM 4, and then finally to Schoenhagen-Strassen at 50,000 digits. And you can imagine that right now 50,000 digits is a lot of digits, right? So I think it remains more as a theoretical curiosity than a practical application at this point. Okay, of course that might change in the future. Okay, so that's a summary of multiplication, and that brings us to the conclusion of. I thought the summary was here, but maybe it's not. No, it's fine. Yeah. So that finishes up our discussion, divide and conquer, and to quickly go over, right? We started with 2 simple problems: binary search and exponentiation. Then we went to sorting, and somewhere in the middle we learned about recurrences, solving them, how to solve recurrences, how to do summations, and how to apply the master theorem. Then we learned quicksort. Then we said, okay, any comparison-based sorting is going to take O of n log n time. And then we went right back and said, no, we are going to do better than O of n log n, and gave you this radix sort. Then we talked about selection, which instead of sorting the whole array, simply wants an nth element. And then we also talked about priority queues, which again, instead of sorting, is something that allows you to do insertions quickly and deletion of minimum elements or maximum elements quickly. Right? So we talked about that. All of those are divide and conquer. And as we went through, we didn't really discuss closest pair. So we said, okay, so far we were talking about non-overlapping problems, but things get gradually more complex and sophisticated. But out here in multiplication, you start dealing with overlapping subproblems, okay? And matrix multiplication, and then integer multiplication. Right? That's what we talked about. Okay? And both of them share this common idea that somehow, the naive approach is going to take, is not going to give you any savings at all. But if you do things in a careful way, then you can get, much better outcomes. Okay, and again, we didn't talk about FFT except to very briefly give an idea of how to go beyond 2 multiple. Okay, so tomorrow night is when you have to submit the